Okay, I had asked you to read ahead a little bit because we're starting something that's a little where really the rubber hits the road in thermo. What we studied so far, what we've studied so far is just kind of the background stuff. Like in English, you learn how to spell, you learn sentence structure, you learn how to make a paragraph and capitalization and all that stuff. And then you finally use it to write stories, right? Or to be able to read properly and all that sort of thing. Thermo is kind of the same way. We've talked about the basic ideas. We've talked about PV equals nRT and gas laws and all that kind of stuff. We've talked about how gas does work and all that sort of thing. So we're going to talk real briefly about the second law of thermodynamics, and then we're going to talk about how this all gets put together and what they actually use it for. All right? Before we do that, we're going to do one quick review. Okay, everybody on page 8, let's make sure that we remember what we've talked about so far. So on page number 8 of your review packet, there is a table at the bottom for all the special processes, isochoric or isovolumetric, adiabatic, isothermal, isobaric. For each one of those processes, I want you to fill in that table with pluses and minuses and zeros, whether the work is positive, negative, or zero, whether the temperature change and internal energy change is positive, negative, or zero, whether the heat exchange is positive, negative, or zero, okay? Do those. Make sure you and your neighbor all have the same, everybody at your table has the same values in there, okay? All right. Let's see what we got. Let's start with process number 1. Process number 1 looks like this. Okay, what's that process called? Isochoric or isovolumetric or constant volume process. Any of those words means the same thing. Okay? Okay, so we have delta T, delta U, what do I have next? W and Q. All right, for process number 1. All right, delta T, plus, minus, or zero?
Negative.
Negative, because we're going down in PV value, right? Okay? How about this one?
Negative.
Negative, because since this is delta U equals 3/2 NR delta T, these always go in the same direction. Okay? How about work?
Zero.
Zero. That's the special thing about a isovolumetric or constant volume process. Okay, so if that's zero, then what's Q?
Negative.
Negative, and not just any negative. What negative?
Same.
It's the same negative as this negative, right? Those two are the same. All right, let's go with number 2. Number 2 is this one. Okay? Process number 2. All right, how about temperature? Negative, but wait a minute, how can you tell?
Because it doesn't go all the way. It's not on the.
The volume is increasing.
Because when you look at this P...
It's lower than isothermal.
Yeah, because there is an isothermal shown, right? So you know it's lower, so it's moving to a lower isotherm. Or if that isotherm wasn't drawn, you would have to take this P times V value here, and this P times V value here, and see which one's bigger, right? And it turns out that this P times V value down here is less than that one, so the temperature goes down, therefore delta U, it goes down in energy. How about work? Negative, because it's to the right. It has area, but that area is to the right, and work equals negative P delta V. We have a positive volume change, therefore negative work, right? Q then?
Zero.
It's 0. Why is it 0?
Yeah.
Yeah, exactly, because the paper said so. Very nice. Because it's an adiabatic, right? And by definition, an adiabatic curve or process, whether it goes this direction or this direction, doesn't matter, the Q is 0. Therefore, these two numbers are the same, right? Okay, number 3. Number 3, we have one. Let me do a different color. Number 3 looks like this. Temperature,
0.
0, because it's an isotherm. So therefore, 0 here. Work is
Negative.
negative. Therefore, this is
Positive.
positive, and these two are the same. All right, and our last one looks like this. It's to the right. All right, this was the one that doesn't have anything 0 in it. All the other ones had something 0. So this one, the temperature change is
Positive.
positive. Therefore, positive energy change. Work is negative. Therefore, Q is, and not just any positive, right? It has to be a very large positive because it has to be bigger than this work to give you a positive number here. Because delta U equals Q plus W, so you have to, since that's negative and that's positive, you have to have a great big positive Q. All right? Okay, how are we doing? We doing okay? Excellent. All right, so that brings us to a mixed up paper apparently here. What the heck? I got all my papers messed up here. All right, that brings us to page 9, and we're going to talk a little bit about entropy. Okay. Dun, dun, dun. We'll have our little story of entropy. All right. Molecules are in constant random motion, right? Okay? But since they're in random motion, how many of you are in statistics? Any of you? Yeah? A couple of you. Okay? And since they're in random motion, they don't all have the same velocity. So they have a velocity distribution. Okay? So this is velocity. Velocity is bigger. This is the number of molecules that have that velocity. All right? So on average, they have that velocity. That would be related to their average kinetic energy, right? So some are fast, some are slow, some are in the middle. Most are in the middle. Okay? But there would be a cold object. A hot object would look like this, where it has a distribution like this. So that's hot. This would be cold by comparison. Now, do we have some molecules in the cold object moving faster than some molecules in the hot object? Sure we do. Okay, but on average, the hot molecules move faster than the cold molecules, right? Okay, when heat transfers, if you have a cold object here, and you have a hot object here, then when you put them in thermal contact, the molecules in general are going to be moving faster in the hot object. So these collide with those. Now, is it possible that a fast-moving one over here will collide with a slow-moving one in the hot?
Yes.
Sure. That means that if you run down the hallway and you're running fast, and there's someone in the hallway moving slow, and you run into them, which way does the energy transfer?
From you to them.
Yeah, from you to them, right? Okay? So what happens is it's possible for heat to flow from cold to hot. If a fast one here hits a slow one here, right? But in general, what's going to happen? You're going to have many more fast ones here hitting many more slow ones here, right? So when you put them together, heat's going to flow from hot to cold always. Okay? The net heat will always flow from hot to cold. All right? Now, what happens then is that this normal distribution here, these molecules start to slow down, these start to speed up, and then what happens? Well, eventually the curves will overlap. And when the curves overlap, then heat transfers between the objects at the exact same rate, or the net heat transfer is 0. And the objects are said to be in thermal equilibrium. They have the same temperature. They have the same average kinetic energy. They have the same average velocity of the molecules. Does that make sense? Okay. All right. So heat flows from hot to cold always because of the randomness of the motion of the molecules. All right? Now, that's one of the consequences of the second law of thermodynamics, that idea. All right? So, when you hear about the second law of thermodynamics, you'll always hear the term entropy. Okay? Does anybody know what entropy is? Okay, chaos or disorder is the most common answer we get from students. Okay? It's a measure. Objects have a lot more entropy than cold objects. All right? Because there's more disorder because the molecules are moving around much more randomly than when you're cold. The colder you get, the less they move, the less disorder there is. Okay? Now, there is a term in physics called change in entropy. Some books will list it as delta capital S, but I'm just going to write change in entropy. All right? And the equation for it is Q over T. All right? What's Q again? Heat. Okay, so heat moving into or out, and T is temperature. So wait a minute. So temperature's in Kelvin, right? So this is always positive. Heat can be positive or negative. So entropy change, the change in entropy of something will be positive or negative based solely on whether the heat flows in or out. Very nice. So like if you walk outside this afternoon on a hot day, will your entropy go up or down? Up. If you walk outside on a cold day, your entropy goes down. Okay? Because you're losing heat. Okay? Now, most students have heard the term of entropy and they hear disorder and they hear that entropy always rises. Okay? That's true when you look at the big picture. Okay? But for an individual object, entropy can go up or down. Okay? So like you walk outside on a blazing hot day, your entropy goes up because heat flows into you. Okay? But what happens to the environment around you? Why does it go down?
It's giving you heat.
Because it's giving you heat, right? And so its entropy goes down. When you put food in the refrigerator, the entropy of the food goes down. But that heat comes out of the food and goes into your kitchen. And the entropy of your kitchen goes up. If you add up all the things that are exchanging heat, then what happens is the entropy at best will always stay the same or rise. Okay? So you get to more and more disorder. It turns out the reason why that is because, for instance, if I take a baseball here, I don't have a baseball around here, do I? Here. Closest thing I have to baseball. If I take this roll of tape, right now it has what kind of energy? Potential, right? If I drop it, it turns into kinetic. And now it's turned into... Okay. It's turned in from an ordered type of energy, an energy that depends on a specific location, to a ordered type of energy where all the molecules are moving together. So all the molecules are placed here, all the molecules move together, and then when it hits the ground, all of that uniform motion turns into random motion. Because the molecules hit the ground and they start to bounce around and they're not all going in the same direction anymore. Does that make sense? It turns out that all other types of energy are ordered or uniform, organized type of energies. But thermal energy is the one and only disordered or random type of energy, and it turns out that all ordered or organized type of energy can turn into randomized energy, but not back. Not very easily. That's why entropy or disorder always rises. Okay? That's why it always rises. If you take a class in college, they'll talk about that, and they'll talk about how it has to do with statistics and the fact that there are so many different possibilities for disorder than there are for order. Like for instance, when I throw this across the room, all the molecules have to move together, right? That's one condition. But there are so many other conditions where they're not moving together. there's so many other possibilities where they're not all moving in the same direction at the same time, at the same speed. Does that make sense? So it turns out disorder is more likely than order. And so energy degrades into disorganized energy. All right? And so all types of energy will eventually degrade into thermal energy. All right? So like for instance, the first law of thermodynamics would say that if I take this and I drop it, it starts with potential, it turns into kinetic as it falls. When it hits the ground, it turns into thermal. Okay? But in the first law of thermal, there's no reason why it can't go the other way. Like for instance, I've got this sitting right here. Okay? And then all it's got is thermal and some potential because it's above the ground, right? And then let's say it just decides to have all its thermal energy turn into kinetic. So it would cool down and fly across the room. So we see things that go like this and hit the ground and warm up. But we don't, that's natural. But we don't see things that would be where it would cool off and spontaneously fly into the air, right? Because that would be going opposite to rising entropy. Because what happens is you would go from disorder to order. And that would be a really, really dangerous world, by the way, if things would just randomly start to cool off and decide to climb up a hill or fly across the room. Or you're sitting in your chair and all of a sudden your chair gets cold and it starts sliding across the floor.
You trying to drink some ice?
If you return, like in a cycle or something, return back to where you began at the exact same initial states, you can, with no friction and all that, you can have no entropy change. But that's pretty rare usually. What usually happens is in any process there can be entropy change. The key thing is if heat goes in, then entropy goes up. So let's look right over here and add a new column. What's the entropy change? All right, for this one, process number 1, entropy goes up, down, or stays the same?
Temperature is negative. Changing temperature is negative. Stays the same.
Okay, but now look, the change in temperature is negative, but what we're interested in is the temperature. So we would be like, this is like the average temperature. And the temperature is always going to be positive, right? It's not the change in temperature, but the temperature. The temperature is always positive. So what are we really looking for?
Q.
Q. Okay, so we have negative entropy change. That means the entropy of the gas went down. That means the entropy of the gas went somewhere else, right? To the environment. Okay, right here the entropy change is 0. Right here the entropy change is positive and positive, right? Because all you're concerned about is, since the temperature of the cycle is always going to be a positive number, even if it's changing, it's positive. Okay, the value is positive. Then all you care about is whether heat goes in or out. So the air conditioner runs. Our entropy goes down because it's taking heat out of us, right? And then it goes outside. And so the entropy of the environment goes up. And in the winter time, it's just the opposite. We pump heat in here, makes our entropy rise, and takes entropy away from something else. Okay? It takes that heat from someplace, gives it to us. All right? Question, comments? All right. The only time entropy will stay the same is if it's an isolated system and you don't have any heat transfer. So that's why right here, since there's no heat transfer, entropy stays the same. All right? Okay. That is an entire semester of entropy in college, all on one page. Okay? There's like all kinds of consequences of the second law of thermodynamics and entropy that we won't get into, but if you want to study them, they're actually pretty amazing. Entropy will show up in chemistry, right? Entropy shows up in biology. Entropy shows up in almost all forms and facets of science. Okay, now that we've covered all the basics, what the heck do we use this stuff for? What's the point?
It's all a lie.
It's all a lie.
Nothing like physics. Yeah.
I mean, we talked about energy, you can use it to solve some problems, understand some things, but what the heck? Why thermo? Why are we spending so much time on it? Well, the key thing is that thermo is just an extension of conservation of energy, and the second law of thermo tells us that heat always flows from hot to cold. It tells us why. And it gives us some limits on how the world works, right? Now, hot place, cold place,
Air travels.
just right
Close
place. In the Goldilocks place, right? All right, heat flows from hot to cold. Now wait a minute. QH is the heat that flows out of the hot place. QC is the heat that flows into the cold place. Sometimes referred to in books as the hot heat and the cold heat. In case you hear those terms, which sounds really weird. The hot heat and the cold heat, or the heat coming out of the hot place and the heat going into the cold place. This occurs naturally. And conservation of energy tells us, how does that relate to that? Well, they have to be equal, right? So this one equals that one. Okay, well here's the deal. Since this occurs naturally in nature, we want to use it to do things for us, to do work. And so here's what we do. We steal some. Okay? All right? And we make it do work. All right, so here's the deal, everybody. QH, QC, are they still the same?
No.
No. So what's our new mathematical relationship between QH, QC, and work? QH minus work equals QC, or you could say that QH equals work plus QC. They're the same statement, right? Conservation of energy. All right, energy that comes out of this place must go somewhere. I thought that was some sort of weapon.
It's just a giant pen.
Where'd you get your big novelty pen? Pay attention. You're learning. You're walking around the halls with a big novelty pen. All right. Here's what we're going to do. Is we're going to build a device that will generate heat. And as the heat flows from hot to cold, we're going to make the heat do things for us. Okay? Now let's talk real briefly about efficiency. If we want to make this machine be really efficient, then what do we need to do?
Maintain a difference in temperature.
We got to maintain a difference in temperature, and the higher difference in temperature we have, the more heat we're going to have flow, right? So that'll be useful. But is this a 100% efficient machine?
No.
Okay, efficiency is equal to what you want, the useful stuff that comes out, which is work, divided by the energy you began with, which for us would be QH. Okay, that's our efficiency. The useful stuff that we get out divided by the total amount of energy we began with. All right? This is going to turn out to be a fraction or a number less than 1. Now you can change it to percent if you'd like, but you don't want to use percent when you're solving this problem. Say you start with 10,000 joules of energy and you get 4,000 joules of work out. That means this is going to be 6,000 joules of wasted heat, and our efficiency would be 4,000 joules divided by 10,000 joules, which gives me 0.4 efficiency. Okay, units?
No, not percent, it's just that.
There's no real unit, so you can leave it like this, and sometimes that disturbs people, so they'll turn it into percent. 40%. But remember, if they say the machine is 40% efficient, when you plug that number in up here for efficiency, you got to plug it in as a decimal, right? Otherwise it won't work out. All right, so 0.4 or 40% efficient. Okay? If I want to make this more efficient, what do I need to do? I got to increase the work. If I want to make it 100% efficient, what I got to do? I've got to do this. I've got a hot place, I've got heat coming off of it, and all the heat goes into work. And then nothing comes out to the cold place.
So then there would be no difference in...
That would be 100% efficient. Now, this violates several things.
People would die.
People wouldn't die. Yeah, the world would end. We'd cause a black hole. Death and destruction. Raining cats and dogs. Yes. Now, this is impossible. The reason why it's impossible is, think about it for a second. If we got a gas up here that we heat up, and then we make it do work for us, and we take all the energy out of the gas, then what will the temperature of the gas be at the end?
Because they didn't pour it, no, it went.
Can't be absolute.
Well, yeah, there's our problem, is that it's got to be cold. How cold? Absolutely cold with no energy left, which means absolute zero. So can we get that gas to absolute zero? Okay, so we got a problem right there. We cannot get the gas to absolute zero. All right? So that's problem number one for why we can't have a perfectly efficient machine. Problem number two is, remember the second law of thermodynamics? Heat flows from hot to cold, right? So our machine, like our car engine, okay? We got our car, our engine's inside here. Our engine, we explode gasoline in there to make really hot temperatures, okay? So this is really hot. And then the heat, as the gas expands, it cools off as it pushes the pistons and makes our engine move. And us with it, because we sit inside. Okay? Now when that happens, how far can the gas cool off to? Okay, what does the second law of thermo say? Heat flows from hot to cold until when? Until you reach equilibrium, right? So if we heat these gases up here and we let them cool off, to what temperature will they cool off to? Yeah, whatever the environment temperature is, right? Okay, so the best we can do is get these things to cool off to the environment temperature. We can't get them to magically cool off to lower than that, right? Right? If you take something hot and stick it outside on a winter day, it's not going to cool off to less than what the temperature of the snow is, right? It can only cool off to what the outside temperature is and no more, right? Or no less. So we have a practical limit because we can't get to absolute zero, and we can't really even get to absolute zero for practical reasons. We can only get to a certain low temperature. Hey, wait a minute. But on a cold day, in the summertime, our engine is hot, but the outside is hot too, right?
The engine's still hotter though.
But the engine is hotter than the outside temperature hot, right? But if you, on a cold day, run your car, and the outside temperature is cold, shouldn't the efficiency of your engine be greater then? Because wouldn't you have a greater delta temperature? And so therefore the gases inside the engine, when you get them hot, should be able to cool off more, right? And should get more efficiency, right?
Except some of the heat also leaves. The more heat leaves.
Turns out you will get slightly more efficient in the wintertime. But it turns out it's not a whole lot because there are other issues going on. Like it takes a little while for your engine to warm up to run properly. So you lose efficiency there. But if you let your car run for a long time on a winter day, it'll be more efficient than if you ran it in the summertime. Okay?
So you take away the heat from the environment.
Yeah, so if you can make the environment a colder place, your engine will run more efficiently. That's correct. If you can make this, the colder you can make this cold place, the more efficient you can be and get more work out of the device. The other thing is we can't build a device that's perfect with no friction. Because devices with friction Well, they lose energy to heat, right? So we have several practical reasons why we can't get to 100% efficiency. Number one, it breaks the law, and number two, it's not practical. Okay? It breaks the second law of thermodynamics.
Maybe a Sharpie.
That's not a Sharpie.
I know, but it's a lot.
Do you need a Sharpie?
Do you have a Sharpie?
I have one.
Sharpie would be great.
Let me see. Daniel, you've got one. I think I got one in here, but maybe not.
Yeah, he's prepared. Yeah, so I'm just,
You know what? All I got is the same thing you have. Yes.
We didn't see that last year.
It's a heat.
Well, that's so cool.
Okay, this is a heat engine right here.
Oh, it is slowly. Look at that.
After the heat.
Okay?
It's not efficient.
It was running really fast before. This is called a Stirling engine.
There's no difference.
Okay? It's called a Stirling engine. And it's running on this power supply to this computer right here. Because the power supply, it gets warm, right? And so you have a warm place right here, and the environment is colder than it. Okay? The hotter this gets, the faster this will run. Or the bigger the difference in temperature, the faster it will run. So what it's doing is it's sucking heat energy out of here, and it's making that motion. That it's doing work. The work is just for it to spin this device. Okay? And then it's transferring the heat from here to the environment through its device, and it's stealing some of that energy to do work. Okay?
So if I turn it on, it'll go faster.
Wait.
Actually, yeah, if you could turn on. All right.
Wait, so
Put
to make it spin backwards, but can you put like a cold cup under it? You're welcome.
If you put a cold cup underneath it, will it spin backwards? I believe it will.
Yeah,
I think so.
it does. Yeah, Carter.
Okay.
Is that what it did?
Yeah.
I
Yeah,
think
he
that's where I
did.
got the idea from.
Yeah.
Anyway, it was running really fast earlier. It slowed down a bit because as it runs, the device itself starts to warm up, and as it warms up, it expands and gets a little more friction. One of the reasons. But if we can get this thing to run, then get this to warm up, it'll run faster. So if you stick it over like a hot cup of coffee,
You want to light it?
no, we better not. I don't want to break it. Anyway, a Stirling engine is an external heat source engine. Your engine in your cars, or
internal.
yeah, those are internal combustion engines where they generate heat inside the devices themselves. This is an external heat source engine where it just takes heat from the environment. So all you have to do is get something or make this bottom plate hot,
Can you put it
and
on
it
your
will run.
hand?
Yeah, it will run on your hand, but it will run much slower.
So what if you put that in a car and it was on a hot day? Could you run the
Probably won't run it out.
engine?
As long as the bottom plate is hotter than the top plate, it will run.
Oh, okay.
Put it on the one for the.
Put ice on it.
Is that one?
Oh yeah, is this one warmer? Yeah, need to go.
I'll work the camera. Scooch it.
If I set it right here, it'll eventually come to rest. Okay, oops, can you see it?
Of course, as it is, eventually it'll come to rest pretty much anywhere because it'll eventually take up the heat.
Yes, like for instance, if this device was turned off, and so this wasn't anymore transferring energy, and it was just warm, but it wasn't continuing to warm itself back up, then when I set it on there, eventually it would suck all the heat out of it, and the whole thing would come to rest. Okay?
Of course, even if that kept the same heat, eventually that would take the heat of that, and so then
Yes.
there would still be no difference.
So now it's slowly coming to rest.
Yeah. No,
Okay, so if you stick it in your hand, so we can get it to warm up, or I forget which way it was going. Was it going that way?
No, that's. I don't think so. I think it's right.
Is it going that way?
Yeah, it will.
I should make one of those.
All
You
right.
hear that, Mr. Brewing?
What?
They're like, he's the awesomest teacher ever.
All right. Oh no.
Well, it's because let's put your hand maybe it's
Well, can you do this? Can you do this with your hands, cause friction, and then put it on there?
Yeah, you could do that. I'm gonna set it back on here and see if we can get it going again.
No. I want to try that. I want to hit my hands and then put it on there.
All right. You mind around there?
Should get back.
Oh, just back. Excellent.
I want to put my
All right. Now, let me show you the cycle. See if I remember the cycle for an internal combustion engine. Okay? So you can get an idea of what it looks like. If I can remember it. I don't know that I have it written down. Here you go. So here's a PV diagram. All right? And you have your cylinder. Okay? And inside your cylinder is your piston. Okay? All right, we begin by opening up the valve so it's vented to the atmosphere. Okay? So the little valve up top here opens up. When the valve opens, you begin right here at standard pressure and standard volume, or standard temperature and pressure, and then that's the volume of the open cylinder. All right?
Yes.
Actually, you know what? We start off, hang on. We start off with the piston up top. Sorry.
Yeah.
Piston starts off up here. All right? And then the valve is closed, so we have an isolated, sealed environment, and then the piston moves down. When the piston moves down, its volume goes up. Okay? Oh, you know what? I could have kept it down there. The valve stays open. I'm trying to remember it. It's been a while since I've drawn this one. So the valve stays open, it goes down, and then once it goes down, the valve closes. Okay? So valve close. All right? And it's down here. All right? When this has moved down, it has been filled with this gasoline vapor, and air mixture that's flammable. All right? The piston moves back up then. So now the valve's closed and the piston moves back up. When the piston moves back up, what happens to our pressure when our volume decreases now that the valve is closed? It goes up, right? So you get this, okay? Actually, I shouldn't draw it so steep because we won't be able to do the top part of it. It goes up like this, all right? And it goes back to this same spot here. But now we're at a much higher pressure. Now when it does that, it does it very quickly. When it does it very quickly, the pressure increases, the volume decreases, and the temperature goes up because it's done quickly. And this is generally very close to Q equals 0. So what kind of process is that? Adiabatic. Okay, now when the valve has gone up, the valve's up here, or the piston's up here, and then you ignite the gases. When you ignite the gases explode, and then what happens? The piston gets pushed down, but even before the piston gets pushed down, when you explode the gases, the pressure jumps up. The pressure jumps up. Now, it won't go exactly straight up, but we're going to assume it goes straight up. Like it explodes, instantaneously we have hot gases, okay? This is an isovolumetric or constant volume process, approximately. So work is 0 for that part, okay? Now, I want to ask you right here, when we go from here to here, that required, is the gas doing work, or are we doing work on the gas? How do you know? Because the volume decreases and it takes effort to compress the gas, right?
Yes.
And then you ignite it and you move up here to even higher PV temperature, right? Okay, now that it's ignited, now it pushes the piston down. When it pushes the piston down like this, and we have another very fast, no heat transfer, adiabatic process. But now this time, are we still doing work on the gas, or is the gas doing work?
Yes.
Gas is doing work. Which is doing more work? Our work on the gas, or the gas doing work?
Yes.
Gas doing work. So we're getting a positive amount of work out of the gas. How are we able to get a positive amount of work out of the gas? Because we ignite the fuel to raise it to a higher temperature and pressure, right? So then when it moves back, the piston back down, we get more work out of the device than we put into the device. Notice that we have had to add heat. Heat goes in, and then so we can get positive work out. So we have a negative work here, but we have a greater positive work, positive work on the gas and negative work here, which is work on the environment, right? I wrote them backwards. Once it expands all the way out, the valve is opened. The valve is opened, it drops back down here, and it cycles back across here and back in order to exit and to evacuate the gases that have been burnt, and then it starts all over again. So it goes up, all right, get the fuel in, compress it, explode it, it goes down. This is called the power stroke, where it generates power, and then it goes through the cycle one more time to push all the old burnt up gases out, and then it starts over again. So this section down here cancels itself out because it goes out, starts over here, goes down here, and then goes back, and then starts again. Okay? Now, how much work is done? Well, that is the work of your engine. Okay? That's the work of your engine, pushing your car around, making things happen, generating electricity for your radio, making the lights work. Say that again?
The area in between the curve.
The area in between the curve, or in the middle of the cycle.
That's the cycle.
That's the cycle. This part right here doesn't really do anything because it cancels itself out. Okay? And that's the cycle. All right? So that PV diagram, those random PV diagrams we've been drawing, those are models for like a real cycle. This is a real cycle.
How would we actually find that?
Good point. Will you have to find that? Well, yes and no. All right? By the way, this is called the Otto cycle, not the AUTO for your automobile, but the OTTO cycle. Otto cycle. All right? All right. So, what would you be expected to do on the exam? You won't be expected to do any kind of calculus. You won't be expected to essentially generate the PV diagram unless they tell you what the processes are. Okay? So like for instance, they might ask you a question like this. Here's your PV diagram, and they start you off here, okay, at point A, and they say that the gas is let's see, which process do we want to do? Let's do that. Let's say the gas goes from A to B, and they give you that part. And then they say, that's from A to B, and then they say the gas expands isothermally to the original pressure. Okay, so everybody sketch, what would it look like if they go from A to B, and then they say C, they go to step C, where the gas expands isothermally to the same original pressure. Okay? Sketch it. I know, it's a lot of effort on your part, but I'm sure you can do it. Really. That sucker's moving really fast now, isn't it?
This is cool.
Okay, so what's it going to look like? It's going to look like an isotherm, right? And it's going to expand. So could you have an isothermal compression? That would go this way, right? But we have an isothermal expansion, so it goes this way, right? So we're going to follow an isotherm, and we're expanding from this point out to the original pressure, right? So that's point C. And then they could say, then they bring the gas at isobarically or at a constant pressure back to the original position. So then you would go like this. Okay, so they're going to use those magic words of adiabatic or isothermal or isochoric or constant volume and constant pressure isobaric, okay? And so you'll be able to sketch what it looks like. All right? Okay, so they might ask you to sketch it like that. They might ask you to actually come up with some numbers for what's going on. All right? Now this one, we're not going to be able to find the area inside. So let's do one that we can find the area inside. I have an example in our handout, but let's do a different one. Let's expand that and see if we can figure out what we're looking for. Okay, so I'm going to make up a PV diagram cycle. PV. So let's do a heat engine. So which way is the heat engine going to have to circulate? Clockwise around, right? So let's do a nice little, we're going to do a triangle or a square. I don't care.
Square.
Square? All right, we'll do a square. Otherwise known as constant volume and constant pressures, right? Why don't we start up here at A, then B, then C, then D. Let's give ourselves some numbers. So we actually are going to solve it with numbers this time. So why don't we make this 1e to the 5th pascals, and why don't we make this 4e to the 5th pascals. All right? Then why don't we down here, why don't we make this 0.01 meters cubed and 0.05 meters cubed. Okay? That sound good? All right, so let's do this. We're going to split this work up. We've got 4 tables. All right? And so we have 4 paths. So what I want you to do is AB, BC, CD, and then D back to A. I want to know what's the change in temperature, what's the change in internal energy, what's the work, and what's the Q for each one. Okay? All right? So let's help each other out, at least to start. The change in temperature. That means that we've got to find the temperature of each individual point, right? For A, B, C, and D, right? So let's do A real quick. What's the temperature at A? How do we find that? Say it again? Oh yeah, we need number of moles. Okay. Excellent question, or excellent comment. Let's make our number of moles, how about 1?
Yes.
2.
Okay, how about 2 moles, just so it's not 1. About 2 moles of gas. Okay, now that we have the number of moles of gas, can we find the temperature?
Yes.
Okay, because we have PV equals nRT at point A, so we want the pressure and volume at point A. So we would do 4e to the 5th pascals times 0.01 meters cubed. N is 2, 8.314 for our gas constant, and the temperature at point A. So hopefully I have a number that's reasonable.
240.56.
What is it?
240.56.
240. 241-ish, right?
Yes.
Kelvin. All right, so that's kind of cold, but we'll be okay. It's an imaginary engine. All right? Hey, let's not do any crazy amount of work. Without using your calculator, can you tell me what's the temperature of B? Oop, that was the key. What is it?
5 times.
Why 5 times?
Increase your volume by
Because we have a change in state problem for which we have PV equals nRT, but that and that and that are staying constant when we go from A to B. And we're increasing the volume by 5 times, so the temperature should increase 5 times, right? So what's our temperature at B?
1,000.
1,000 what?
202.
200,
Well, 203.
203?
Somewhere on there.
You know what? Let's make, just so that the math is easier for us, let's round them to this. Okay? That's just going to make our math a little bit easier. All right? What's the temperature at C?
Down.
Okay, now our volume is staying the same, but we're going down in pressure by a factor of 4, right? So I got to divide this by 4, and I get 300 Kelvin. Is that right? Okay, so now I go from here to here, and what do I do?
Divide by 5.
Oh man, now I'm going down in volume 1/5, but that's staying the same, so
60.
wow, that's only 60 Kelvin. And then let's check it to make sure. If I go from 60 Kelvin to here, I have to go up 4 times. So 60 times 4 is 240. So we're in good shape, right? Excellent. All right. So now, everybody, now that we found the temperature of each individual spot, then what's delta T, what's delta U, what's work, and what's Q? And I want, let's do this. Let's have this back table. You're AB. This table here is BC. This table here is CD, and this is D back to A. And yes, you'll work with this table, and you'll work with that table. All right. So the pressure's on.
No pun intended.
That's right. The pressure and temperature is on. Okay. Make sure you all get the same answers for everything.
Yeah. To PA converter. I got 4,189.
11325, dude. ATM.
I'll go right down the board. Wait, what's it got? All of them?
All about
835?
all about.
101. 101,325. Yeah, don't use 100,000. That we only use that. Yeah, that'll give you an error. Because if you're off by more than 1%, the computer will count you wrong. Alright. We'll be good for work.
Shouldn't R work be the opposite of
Because the pressure is and then you multiply by the delta of the
No, I got that.
I don't leave much room for AB. So,
and that's going to be negative.
Wait, is that work zero? Since we're going straight up, is that work zero? Is that work zero since we're going up? Yeah?
Hey, Jonathan, you're changing using multiple.
They didn't multiply by both.
Sorry, then you just have to work.
when you do what?
You didn't multiply by both.
I'm pretty sure I did, because it's 3 over 2 times 2 times the...
Times 180.
It doesn't have to be
times 2 times 8.1314
Yeah, zero work.
times negative 900.
Volume.
It's 1.5
I was asking if I can see.
They got negative.
Ours should be the opposite of that.
The one we did. Oh, delta U or Q is the same.
Obviously, wait, what was theirs from B to C? Theirs was 900. Theirs was 600. Oh, well, it's true though. Because it's from 1,200. It is 900. It's just that, remember, we started at a smaller pressure and volume than they started, and we increased just one. So obviously, they changed the way.
They have the same pressure.
Yeah,
Mark, bad here.
Me and my stuff blowing up matches that.
This one really bad? But it's purple.
Purple means the board.
Yeah, Mr. Board.
All right.
looks.
You, Colin?
It just
Color. Eventually, theirs has to be.
stays here.
All right, so everybody at your table agreed with the number, right?
Yes.
Excellent.
So he needs to get 40. No, that's not. Somebody's wrong.
Best group. Oh, look at that.
Somebody's wrong. It didn't add up to 0.
Because we're rocking that purple.
Because I plugged it in. Because we have negative 900 for temperature.
No, something's wrong because the temperature don't add up to 0.
Temperatures don't add up to 0, the temperature changes?
Changes don't add up to 0.
Well, we rounded, so it was off by only 20, and we rounded on all of it. Yeah, well, those numbers are right.
Yeah, their numbers are rounded as well. Somebody's negative when they're not, and somebody's positive when they're not. That's what's going on.
Yeah, we got a sign issue going on here somewhere.
So should...
All right, let's check.
Does it need to be positive then?
All right, well, let's check, everybody. Okay, going from A to B. Going from A to B, we're going up in temperature. A to B.
C to D is should be negative.
Yeah.
Uh-oh.
C to D should be a negative 240. That's so cold.
We have everybody else pay attention here. We're going up in temperature here. We're going down in temperature here. We're going down in temperature here. So,
Negative 240.
okay, this one should be negative. That's going to make this negative. Okay? We'll see if everything else is correct. All right, and then we should go up in temperature, right?
Yeah, it's 0 now.
So this should be positive and positive, negative and negative, negative and negative, positive and positive. All right. Now, we have a cycle, everybody. Actually, well, you know what? Let's just make sure these look all correct, too. We go to the right. That's negative work. So that looks good. Notice the units, kilojoules. That's fine, as long as you label it. B to C, no work. C to D should be positive, but should be less than this one. That looks good. And then from D back to A, we should have 0 again, right? Because it's vertical. Okay, and then these, let's make sure those look right. We have positive here and negative here. This is going to have to be positive and a big positive, which it is. If that's negative, then this one has to be negative because these two added up equals that. If that's negative, and that's positive.
Be a bigger negative.
Okay, this one's going to have to be negative. Yeah,
Bigger
because
negative,
this sign was messed up. It messed up all the signs. All the magnitudes are correct. Okay?
Wait,
Wait,
Q,
no,
that
but
magnitude's not
it's
correct. It
yeah,
has to
delta
be-
U minus a negative Q would be
Oh, is that right?
minus
Hang on.
4,000.
Let's just find out. Just find out.
Q should be greater than negative.
Delta U equals Q plus W. Let's make sure. If I have a negative 5,986 equals
So it's 9,056.
something plus 4,000.
So minus 4,000 is negative
Yeah, it's
9,986.
Yeah, negative.
9,000.
9,000.
Yeah, see?
900.
Whoa, negative 9. Oh, because that messed it up. So it's negative 9,000.
986.
There we go.
Yeah.
See? Not best group, because y'all missed it.
Lower than negative. Right.
You?
Hey, Rudy. Dude, no taunting. We're all working together here. All right, and then we go up in temperature, so that's positive, and these two should be the same because that's negative. Very nice. Okay?
That's zero.
Very nice. Okay, so let's do a couple of checks. When we go all the way around the cycle, we should have a net temperature change of 0. So if I add that to that to that to that, does it add up to be a temperature change of 0?
Yes.
Okay. When we go all the way around a cycle, we should have no energy change. No net energy change. So does that plus that plus that plus that add up to be 0? That adds up to be 0?
Yes, approximately. Depending on 8.4, I think.
It's about right.
But only one person's working it? Come on.
0.
Yeah.
0? Okay, let's talk about sig figs real quick. All right. No, overkill. Overkill, overkill, overkill. Y'all had overkill. All right? We need to round these things. We're going to let it slide this time, but when you're pulling numbers off a graph, now realizing that I only gave you one sig fig,
That's pretty.
right? Which I should have given you a little bit more than one sig fig to start. But you certainly can't generate 1, 2, 3, 4, 5, 6 sig figs from just one, right? Okay, so, I mean, I didn't give you enough sig figs, but you definitely have too many here. All right, now, hey, what's the work for the cycle? It should be this plus this. Should be negative
It's negative 12,000.
Yeah, it should be-
12,000 joules.
You just find that due to the area.
All right, and let's check it. Is the area
Yes, it is.
12,000 joules? It is. Okay, now let's add all these up. Everybody add these up. What do you get?
12,000.
Really?
Yes.
So it should be.
12,000 joules. Now does that make sense?
Yeah, because delta U.
When delta U is 0, then these two should be the same, but opposite sign, and they are. All right, we're looking good. Now we have calculated every possible thing, almost. Let's find out what that looks like on this diagram now. The QH comes from the hot place, QC goes to the cold place, and work comes out. This is the heat that goes into the cycle. This is the heat that comes out of the cycle. So you might want to rename this as heat that goes in, and this is the heat that comes out. Okay, this is the work. What's our work?
Negative 12,000.
12,000 joules. Now I'm just going to leave it as positive 12,000 because I'm just doing magnitudes here, okay? So the magnitude of work that comes out, and negative tells me it comes out, is 12,000. Okay, how much heat comes out of the cycle? Which ones of these are coming out?
All the negatives.
All the negatives. This is the QC. Where's the QH? All this stuff is the QH right here. QH. Okay, that side of the room, calculate QH. This side of the room, calculate QC. Okay, QH people, what do you get? 44,434.
32. Okay.
Okay, yeah, I rounded it. All the QC people, the heat that comes out, what do you get?
32,430.
Okay, now let's make sure it works. Didn't we say that in this diagram, how do they have to add up?
QC plus or QC.
Yeah, the two that come out have to equal the one that goes in,
They
right?
do.
And they do.
Whoa.
Nice. Hey, wait a minute. What's the efficiency of this engine?
Work out.
12,000
over
32.
12,000 joules over 44,434.
Yeah.
What is that? Not that great.
27.006%.
Okay, 27%.
Doesn't Dr. Hill say?
Or 0.27. Okay?
That's a bad machine.
That's about what your car is. Your cars are about 25% efficient.
That's bad.
That's not great,
But it works.
but it's not horrible. Actually, they work very hard to get to that 25%. And
Cars work very hard too.
if you want your engine to be more efficient, a way to do it is to make your engine run slower. Don't have any headlights. Don't have a stereo.
Don't have AC.
Don't have an AC.
No power.
Ooh, in the south, that's really bad. Cut holes in the bottom so you can have Flintstone feet making it go. Right?
I'd rather walk than push a car.
Actually, that would be really good. That would be very good because organisms are very
Does that make any
inefficient.
sense?
So
Oh, that's true. We'd have to eat more food and cause more, carbon footprint than if we just burn gasoline.
right.
All right. No. Hey. You have a cold-blooded animal do the Flintstone feet for you because they're way more efficient.
Nah, but even
Alligators,
others-
yeah, whoa.
So just train an alligator.
Not if you make them hot. Not if you get them, lay them out in the sun.
Oh, okay.
Yeah.
The water maybe, but.
All right. Hey. Shh, listen up. All right. We've done everything that we could possibly do with this. The only thing is what I want to show you over here is where the QH and the QC and the work is. Okay, the work is right inside here, right?
Yeah.
That work is this right here, right?
Yeah.
Okay, where is the QH? The QH is here
All the way down.
and here, right? So the QH comes in right here. And the QC comes out these two, right?
Oh, okay. So you're drawing where? Okay.
So it comes out these two and it goes in these two. Notice this one's smaller than that one, and the difference between them is the work that's done. Does that make sense?
Yeah.
Okay, now we could repeat this whole thing in reverse and make it a refrigerator. And if we made a refrigerator, these two would still be 0. But now the work would be positive and the heat flow would be negative. Very nice. Okay, the last thing we're going to do is talk briefly about refrigerators on Tuesday, and we're going to talk about the most magical efficient cycle there never was, which is called the Carnot cycle. Okay? We'll talk about why the Carnot cycle doesn't really exist, but it's an imaginary best case scenario for what you could best do with the efficiency of an engine.